When a car turns a corner on a level surface, it normally follows an arc of length, an arc here, which is path 1, and it is 1/4 of a circle with radius r1. It's shown here. And if we let r1 be equal to 10 meters, what is the maximum speed that this car can have when it performs uniform circular motion on path 1? So basically the car is turning on this path 1, and we're trying to find its maximum speed. So we can set up a free body diagram for this car. So if we set this dot to be the car, there's going to be the normal force acting on it, as well as the force of gravity, or mg. And we're also going to have a static friction force, since it's undergoing uniform circular motion, and we're assuming that it's not, we're trying to figure out the maximum speed it can go before it slips. And this is going to be our static friction, since the car is not slipping. And our coordinate system is going to look something like this. Here we have the radial direction, and of course we have the direction that is perpendicular to the plane of circular motion, z hat, which is where the normal force and the force of gravity act. We also have a component tangential to the circular motion, and we don't have any forces acting on it right now, so this whole part can be neglected. So we can use Newton's second law that says the net force acting on object is equal to the mass times the acceleration of the object. So let's apply this to the radial direction. So the force of static friction is the only force acting in the radial direction, and that is equal to the mass times the centripetal acceleration, or the radial acceleration, which is also equal to v squared over r. And in this case, r is r1. It's the radius. It's the first radius. And we also have an equation that says that the force of static friction is equal to the coefficient of static friction times the normal force. And we can figure out what the normal force is by using another equation, but this time setting the net force for the z direction, or the direction perpendicular to the plane of circular motion. So this becomes the normal force being in the positive z direction minus the force of gravity must be equal to the mass times the acceleration, which is 0, since the car is not accelerating into or out of the plane of circular motion. So from that, the normal force must equal the force of gravity, or mg. So the force of static friction becomes the coefficient of static friction times mg. And we can substitute that back into our equation above, over here. That's equal to mv squared over r1. And the masses cancel. In this, we need to solve for v. And in this case, I'm going to call it v1, since we actually have two scenarios here we're going to look at. So if we solve for v1 is going to be equal to the square root of the coefficient of static friction times g, gravitational acceleration, times the r1, or the radius of this first circle here. So I'm going to erase everything here to make more room here. This becomes the square root of the static friction coefficient. And this is going to be 1, since the maximum static friction coefficient is equal to 1. It's just simply not possible to get a value higher than this. And g is equal to 9.8 meters per second squared. And r1, the radius, is going to be equal to 10 meters. So if you evaluate this, you should get that it is equal to about 9.9 meters per second. So v1 is going to be about 9.9 meters per second. The maximum velocity in the first scenario is 9.9 meters per second. And I'm going to write this equation down. the velocity is going to be, the maximum velocity rather, is going to be equal to, let me rewrite this. The maximum velocity is going to be equal to the square root of gr. And I got rid of the static friction coefficient because the maximum possible static friction coefficient is simply 1. So it can just simply be neglected here, since multiplying by 1 doesn't make a difference. So we can just get rid of that. So that's our first part. Now, suppose the car wants to turn the corner with a higher speed, and it does so by cutting the corner, or performing uniform circular motion along a different path, which is path 2. And path 2 is 1/6 of a circle with radius r2. What is the radius r2 and the new maximum speed on path 2? So I'm going to recreate this diagram. So here we're going to have like path 1. It's not very straight, but it will do. I'm going to write this inside actually, r1. And these two are the same, they're both radii. This is 90 degrees. And the first path is a path like this. This is path 1. We'll call this P1, path 1. The paths won't actually matter, as you'll see. And this is point B, this is point A. And of course, we have to draw the second part. This is really bad, but it gives us a general idea. This is 60 degrees. And this is R2, and this is also R2. This is not to scale, but it gives us a general idea of what to expect. Now, if we draw a line here, we can draw a line here to help us. So from here, you'll notice that this R2, the triangle with a side length radius 2, R2, is going to be an isosceles triangle, since these two sides are congruent to each other. So therefore, there's an isosceles triangle theorem, which says that if you have an isosceles triangle, the angles opposite of the congruent sides are also congruent angles. So these two angles are congruent to each other. And I'm going to call their measures x, x1, and x2. So from the triangle angle sum theorem, x1 plus x2 plus the 60 degrees here must equal 180. And so x1 plus x2 must equal 120. And of course we know that x1 equals x2. So we can substitute x1 for x2, and the same for, we can also substitute x2 for x1. So this then becomes 2x1. Suppose we substitute in x1 for x2. So 2x1 is equal to 120. So x1 is equal to 60. And that is also equal to x2. The value of x2 is the same. So these two angles are both 60 degrees, which means that this must be an equilateral triangle. So all three of these sides are congruent. So this must be R2 as well. So if I erase this to make more room, that is 60 degrees as well. And that's R2. So now if we look at the first triangle, we'll notice that we have a right triangle. And so we can use the Pythagorean theorem. So c squared equals a squared plus b squared. In this case, c squared is R2, the radius 2 that we just found to be this length here. That squared must be equal to a squared, which is R1 squared, plus b squared, which is also R1 squared. So R2 is going to be the square root of 2 times R1 squared. And now we can actually plug in the numbers. That's going to be equal to the square root of 2 times 10 squared, which is going to be about 14 meters. So R2, the radius 2, is going to be 14 meters. R2 is equal to 14 meters, approximately 14 meters. So now I'm going to erase all of this. And now we can actually just simply plug everything back in to calculate a v2, or the maximum velocity for this second path. And again, that's equal to the square root of gr. Coefficient of static friction is 1, so we can remove it. And g is 9.8, and the radius is calculated to be 14 meters. And we're going to take the square root of this expression. So v2, or the maximum velocity from path 2, is going to be 11.7 meters per second. You can see this makes sense, since the radius 2 is larger than radius 1. So the centripetal acceleration will be less, so allowing you to have a greater velocity. So this will be 11.7 meters per second. And that is how you would solve this problem here.